Atomic radius! A science production. What is atomic radius? Atomic radius is the average length from the center of an atom's nucleus to its valence electrons. You need at least two atoms to be able to determine this. I'll discuss why in a moment. And it also has to be measured, or is typically measured in picometers. That's 10 to the negative 12th meters. It's really, really, really small. Remember, we're talking about atoms here. Now, why do you need two atoms to be able to determine this? If you just have one atom, it's impossible to determine where its valence electrons are. Electrons are moving near the speed of light, and they have the duality part where they behave both as a particle and a wave at the same time. So what scientists do is they take two atoms. Let's look at these two examples in their electron clouds, and we try and put them as close to each other as possible. And where they bounce back is because the two nuclei are both positively charged, and there's a limit to how close that they can get to each other. So this distance between two of the same atom's nuclei divided in half gives us the atomic radius of just one. So that's how it's determined. For sodium, it's about 227 picometers. Now, the periodic table allows us to quickly compare atomic radius size, as long as you understand the trends. Down a family, radius increases. So we look at the first family, column 1A on the periodic table, the alkali metals. You can look at the pictorial representation from lithium to cesium, the radius is increasing. But why? Well, it has to do with electron shielding. Electron shielding reduces the Coulombic attraction between the nucleus and the valence attraction, as long as you know what Coulombic attraction is. Well, it's the attraction between a positive and negative particles, and it weakens the further apart they are. I like to compare it to, but it's not the same as, magnetic force. So if you have two magnets that are relatively close to each other, the magnetic force of attraction between those two magnets is pretty strong. Now what happens if you take those two magnets and you move them further away? The magnetic force of attraction is weaker. Well, if you have a nucleus and an electron that's pretty close, the force of attraction is great. If you have a greater distance between those two, then the force of attraction, Coulombic attraction, is weaker. But there's something else that also adds and makes it different than magnetization or magnetic force, is that the Coulombic attraction is the attraction between positive and negative. What about like charges? So if I have this valence electron, but there's a kernel electron layer in here, not only does it shield the outermost electron from feeling the attractive force of the nucleus, but because this electron is negative and this one is negative, they repel each other. So this electron actually pushes this electron even further away. That's what we call electron shielding. So each new period adds another energy level or another layer of kernel electrons. So the amount of shielding increases from top to bottom. If you look at lithium, it's got one energy level shielding its outermost valence electrons. Sodium has two layers shielding, potassium has three, and it increases as you go down. So the more electrons getting in the way or shielding its valence electrons, the further apart the valence electrons of the nucleus, which makes its radius bigger. Now, across a period from left to right, radius decreases. If we take a look at the second period from lithium to neon, you can see in pictorial representation the size of the atom decreases from left to right. But why? It's nuclear strength that causes this trend. So Coulombic attraction from a nucleus to valence electron increases from left to right across a period. Now, it's similar to, but not the same as, magnetic attraction, because shielding is constant, so that's not the reason. So if I have two magnets that are relatively close to each other, I get a force of attraction between them. Now what happens if I keep the same distance but I double the size of both magnets? The force of attraction is even greater. That's similar to what we're dealing with here. Across a period, there's more protons. Lithium only has 3 protons in its nucleus, but beryllium has 4. Boron has 5 and carbon has 6. So the amount of positive charge in the center is increasing. It's getting stronger. That's like the magnet getting bigger. And since shielding is the same, they're all in the second energy level, so they all have the same number of shielding energy levels, 1. That means that the nucleus is pulling on that same level even harder, which causes it to get closer. So let's see if you can pick up on which one of these two is bigger. You can pause the video after each one of these statements to figure out which one you think is bigger, and then press play to check your answers. So which is bigger between nitrogen and arsenic? So look at nitrogen and arsenic. We can see that they're both in the same family. And what determines every trend in a family? It's electron shielding. So arsenic is further down in the same family, so it has more kernel electrons, more energy levels, and more shielding, which means it must be bigger. So arsenic is bigger. The next pairing, manganese and technetium. Manganese and technetium are both, again, in the same family. So which one has more shielding is the one is going to be bigger in atomic radius. That's technetium. The next pairing, boron and neon. Boron and neon are in the same period, period 2. So that means that they both have the same amount of shielding. That's not what dictates the trend in atomic radius across a period. What is nuclear strength. Since neon has got 10 protons and boron has only got 5 in the nucleus, boron has got a weaker nucleus, which means its hold on those two energy levels is less or weaker, so that means boron must be bigger. The next pairing is calcium and zinc. Calcium and zinc are both in the same period, so whichever one has got the weaker nucleus must be the bigger radius. Of those two, the one that has the weaker nucleus is calcium with only 20 protons, so calcium is bigger. The next two, iodine and rubidium. Iodine and rubidium are in the same period, so whichever one has got the weaker nucleus at the same amount of shielding is the one that's going to be bigger. Rubidium has got more, or it's got a weaker nucleus, so it's the bigger radius. And lastly, krypton and neon. Krypton and neon are both in the same family of noble gases. Whichever one has got more shielding is the one that's going to be bigger. Neon is only in the second energy level. Krypton is in the fourth period. So krypton has got more shielding, so it must be the bigger radius. Now, what atom can you determine has got the largest atomic radius of them all, of all the atoms on the periodic table? If you've been paying attention and you understand these trends, you should be able to figure this out. If it's the biggest, that means in a family, we're looking for the most shielding. And in a period, we're looking for the weakest nucleus. So we're looking for something that has a combination of the most shielding and the weakest nucleus. Have you figured it out yet? It's francium. Francium has got the most shielding of all the elements with the weakest nucleus. Now, which atom has got the smallest atomic radius? For this one, we're looking for something that's got the least shielding, so its Coulombic attraction is great, but with the strongest nucleus. The weakest shielding is no shielding at all, no internal or kernel electrons. And it's got to have the strongest nucleus. So we're looking for something with the least shielding and the strongest nucleus. Did you figure it out? It's helium. Helium has got to be the smallest atomic radius. Thanks for watching.